This talk is titled Learning a Stability Filter for Uncertain Differentially Flat Systems using Gaussian Processes. My name is Melissa Greeff, and this work was done in collaboration with Adam Hall and Professor Angela Schoellig at the Dynamic Systems Lab at the University of Toronto. Learning-based control has been shown to outperform conventional model-based techniques in the presence of model uncertainties and systematic disturbances. However, many state-of-the-art learning-based nonlinear trajectory tracking controllers still lack formal guarantees. In this work, we learn a filter that can augment any controller for control-affine differentially flat systems to efficiently certify robot tracking stability and input constraints in the presence of model uncertainty. Intuitively, differential flatness is a structural property that allows us to separate the system dynamics into a linear dynamics and a nonlinear term. So in this case, U is the input to the system. A common control approach for differentially flat systems is to try to linearize the system by using a feedback linearization controller designed based on a nominal system model. A nominal feedback linearization tries to cancel the nonlinear term. In this way, there is a unity mapping between the desired input VD and the input seen by the linear dynamics. An outer loop linear controller is then used to design VD based on the linear dynamics. Unfortunately, performance and safety are limited by the mismatch between the nominal model and the actual system. So in reality, often because of this nonlinear mismatch, there is not a unity mapping between these two inputs. In this work, we make two key assumptions. Firstly, we assume that both the actual system and our nominal model are control affine. In this case, the functions f and g in the system dynamics are unknown, while f hat and g hat are known functions in our nominal model. Secondly, we assume that both the actual system and our nominal model are differentially flat. This means that we can rewrite the system dynamics comprising of a nonlinear term, where the functions alpha and beta are unknown, and a known linear dynamics. We can similarly do the same thing for our nominal model. While both our system and nominal model have the same linear dynamics, there is a nonlinear mismatch as a result of functions alpha and beta being unknown. Related work tends to make one of two additional assumptions. The first is to assume that the actuation function is known, or in other words, that the uncertainty is only a function of the state. And the second assumption is to assume that there are no actuation constraints. And so practically speaking, for the first assumption, there is often uncertainty in the actuation function as a result of delays, errors in the system parameters, or unaccounted dynamics of low-level controllers. And there are often actuation or input constraints that are required to represent physical limitations or may be added for user safety. Our proposed approach considers uncertainty in the actuation function and learns a filter that can augment any outer loop controller to efficiently ensure robust tracking guarantees and input or actuation constraints. Our method requires three key components for our filter. Firstly, probabilistic feedback linearization, where we try to find the most likely input to feedback linearize the system or cancel this nonlinear term. Secondly, a probabilistic stability filter that tries to guarantee tracking convergence with high probability. And finally, an optimization problem that combines probabilistic feedback linearization with the stability filter and input constraints. As previously mentioned, the objective of feedback linearization is to find an input U that creates a unity mapping between the desired command from the outer loop linear controller and the input seen by the linear dynamics. We propose using a Gaussian process to learn this nonlinear term. So we label the nonlinear term psi of A, which takes in inputs Z, which is the state of our system, and U, which is the input to our system, and outputs the input to the linear dynamics. In other words, the nonlinear term we denote by the function psi of A. We learn the nonlinear term as a Gaussian process. And then in probabilistic feedback linearization, our objective is to compute an input that is most likely to result in a unity mapping. One way to do this is to find the input U that minimizes the expected value of the distance between the input V seen by the linear dynamics and the desired input from the linear controller. We propose using the following kernel selection for the Gaussian process. As a result of this kernel selection, the predicted mean for the Gaussian process is linear in the input, and the predicted covariance is quadratic in the input. So by exploiting this kernel selection for control-affine systems, the probabilistic feedback linearization problem is a convex quadratic program. And this can be efficiently solved for you. We propose extending the probabilistic feedback linearization formulation by also including its stability filter that guarantees tracking convergence with high probability. To do this, let's first consider the error dynamics, where E is the error between the state Z and the reference state, and A and B are the matrices that describe the linear dynamics, and Z dot is the derivative of our reference state. We would like to find a control Lyapunov function that satisfies the following two properties to ensure exponential tracking convergence. We propose the following Lyapunov function, where P is obtained from the algebraic Riccati equations. By plugging in the aerodynamics, this decreasing condition has the following form. And we would like this decreasing condition to hold with high probability. So in this case, delta is some small value. We make use of a key theorem for Gaussian processes. And what this theorem says is that under certain conditions, our function psi of A is bounded based on the mean and the covariance of the Gaussian process. And so what this allows us to do is to rewrite this condition in terms of the predicted mean and covariance of the Gaussian process. So now putting this all together. So our filter comprises of probabilistic feedback linearization, which tries to find the input that is most likely to cancel the nonlinear term, subject to a probabilistic stability filter, which ensures tracking convergence with high probability, and input constraints. And the key is that by exploiting the kernel selection, we can rewrite this optimization problem as a second-order cone program. And this is a convex problem which can be efficiently solved. We now compare our approach to related approaches in simulation on a 1D quadrotor, where the quadrotor is just moving in the x direction. So we consider nominal LQR, where the linear controller is an LQR controller, and there is no learning. We consider a robust LQR controller, and we consider our same approach, but with no stability filter in light gray, and our proposed approach in red. We consider the case without input constraints and with input constraints. And we compare our approach based on the average tracking error versus different trajectories that are increasingly more aggressive. And what we see is that without input constraints, our proposed approach has a 90% decrease in average tracking error as compared with the robust LQR approach. And when we compare the case with input constraints, we see that our proposed approach outperforms related approaches when the trajectory is feasible for the given input. And perhaps the most important point is when we compare the average computation time for the different trajectories. The robust LQR approach has a computation time of approximately 0.3 seconds, while our computation time has dropped significantly for our approach and is on the order of solving a QP, so approximately 0.005 seconds. So to summarize, our proposed approach efficiently handles robust tracking stability and input-based constraints in the presence of model uncertainty by exploiting the structure of control-affine differentially flat systems. And critically, our approach has a computational time nearly 2 orders of magnitude smaller than related robust learning-based controllers.